So before we get into this lecture, let's just review a couple of things about heteroscedasticity. So heteroscedasticity means that the variance of the error term varies between observations or individuals. It is no longer constant. It's a problem that's very common in economic data, and it creates problems for us because the Gauss-Markov assumptions will now be violated. Fortunately, we have one very simple way of handling heteroscedasticity, and that is to just estimate the model using OLS, because we know that that will give us unbiased and consistent estimates of beta. We cannot trust the OLS standard errors, but we can simply replace them with robust standard errors or white standard errors, and that allows us to do inference, which is asymptotically correct. That's a very quick way of handling heteroscedasticity, although not the most efficient way. And the purpose of this lecture is to consider specifically this issue. How can we estimate our parameters more efficiently when we have heteroscedasticity? And turns out that we can do that with a method that's called weighted least squares. So this is not ordinary least squares, it's an alternative to that. So the setup is as follows. We have the linear regression model, random sampling, bunch of x variables. It's linear in parameters, not necessarily in data. The explanatory variables are exogenous, so OLS is unbiased and consistent, but we have heteroscedastic error terms, and that creates problems. The OLS estimator, the standard errors are inconsistent, and the OLS estimator is not efficient. So in this lecture, I'm not going to do a complete discussion and cover of the weighted least squares method. I am just going to consider one example. Generally, it's not that hard to modify this example and do weighted least squares on other examples which are not exactly the same as this one. So let's say that I have this simple linear regression model. 2 explanatory variables, 3 parameters. The error term satisfies the following: the expected value of epsilon I conditional xi is 0. Exogenous x variables, we can estimate it consistently and using OLS, which will be unbiased. But we have this nasty little thing of a variance that is not constant. In this example, we'll make a simple assumption. We will assume that the variance of the error term is sigma squared multiplied by xi2 squared. This is an unknown constant. This is of course known. This also means that the standard deviation of the error term is a constant sigma multiplied by xi2. So the idea here is that as xi2 increases, the standard deviation and the variance of the error term gets bigger as well. So based on these assumptions, I want to figure out an efficient estimator of my beta parameters. OLS is not going to be efficient. And here's the idea for the solution. Let's divide both sides of my regression model by xi2. So I do yi over xi2 equal to beta 1 over xi2 plus beta 2 xi2 plus beta 3 xi3 over xi2 plus epsilon I over xi2. For this to make sense, xi2 needs to be a variable that only takes positive values. We are going to call this the transformed model. It's a transformation of the original model. So the good question now is why? Why would I divide both sides by xi2? Well, the error term of the transformed model is this one, epsilon I over xi2. So let's check out the properties of this one. First of all, we see that the expected value of the error term of the transform model, this one just goes outside because it's conditional on xi, so we can treat that as a constant. And by assumption, this is 0, so the whole thing is still 0. So that means that the transform model, or I should say in the transform model, exogeneity still holds. The error terms they do still have a conditional expectation of 0. So let's check the other condition in the Gauss-Markov theorem. Let's figure out the variance of the error term in the transform model. Remember, when we do the variance, we can take out constants if we remember to square them. So 1 over xi2 squared times variance of the error term of the original regression conditionally on xi. Well, our assumption was that this was equal to sigma square xi2 squared. So the whole thing becomes 1 over xi2 squared times sigma squared times xi2 squared. These cancel and the whole thing is just sigma squared. So why is that important? What's the point? Well, the answer is as follows. These error terms, the error terms in the transformed model, are actually homoscedastic. The error terms in the original model were heteroscedastic. These are homoscedastic. We've checked both of these conditions for Gauss-Markov, and that means that Gauss-Markov holds for the transformed model. Not for the original one, but for the transformed model. And notice that I have the same beta parameters in the transform model as in the original one. So I can actually estimate those, but doing it based on the transform model instead. So looking a little bit closer at this model, we see that we have a cancellation here as well. But it's still a linear regression model. It's linear in the parameters, although no longer in the data. So if I want to estimate the transform model, all I have to do is to run a regression where this one, the ratio of y and x2, is my dependent variable. So y divided by x2, that's my new dependent variable, on first 1 over x2. The second explanatory variable will just be a constant, beta 2. So that's my c. Let's write constant here. And the final one is x3 over x2. I know that since the Gauss-Markov are satisfied for my transform model, I know that the estimates I get from the transform models will be efficient. So I will get efficient estimates of beta 1, beta 2, and beta 3 from this model. Also, since the Gauss-Markov assumptions are satisfied, the standard errors will be correct in the transform model. There is no need for robust standard errors in this case. The only thing you have to be careful with is the interpretation. If you run this regression, then the parameter in front of this variable will actually be the intercept of the original model, while the intercept of the transformed model will be the marginal effect of x2. The parameter in front of this variable will be the marginal effect of x3. So here's a simple example. Let's say that my original model, then my y variable is wage, and I have two x variables. x2 is school, number of years education, and x3 is experience. Let's say that we have heteroscedasticity, so that the variance of the error term given xi is, let's say, sigma square xi2 square. So the number of years in school is the variable that affects the variance. Probably not going to be the case, but it doesn't matter. Just want to illustrate the procedure. So the transformed model, then my dependent variable is wage over school, and my explanatory variables are 1 over school and experience over school, and an intercept. So if I run this regression, if I want to do weighted least squares in eViews, I'll just do wage divided by school, intercept 1 over school, and experience over school. Okay, these are my estimates. This is weighted least squares. Remember, this one, the intercept in the transform model, is really the marginal effect of school. This is the intercept, beta 1, and this is the marginal effect of education. These are fine as they are, well, as long as this assumption here is satisfied. And these estimates that we got here are more efficient than the OLS estimates, plus that we don't have to make any adjustment to the standard errors. So what's the drawback of this procedure? Well, the drawback of weighted least squares lies right here. In order to do weighted least squares, I have to have a model for the variance of the error term. Without the model for the variance of the error term, I don't know how to create a transform model. I'm basically just dividing both sides by the square root of this part, which is xi2. If I had assumed instead that the variance of the error term was sigma square xi3 squared, then the transform model would be different and the estimates would be different. And even worse, these estimates would no longer be efficient if I make an incorrect assumption on the variance of the error term. So in that sense, the weighted least squares estimator is very sensitive to an assumption that's often very hard to know if it really holds. contrast that to this simple procedure where we estimate the parameters using OLS and we make adjustment, we create robust standard errors. That method will be fine no matter what the form of heteroscedasticity we have. So to conclude, this efficient method of doing weighted least squares has advantages and disadvantages. If you make the correct specification for the variance, it will be efficient. You will get typically much smaller confidence intervals and better power in your hypothesis tests. But if you make an incorrect assumption about the variance of the error term, the confidence intervals may actually end up being wrong.